Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.2, which is all about absolute entropy and entropy changes. We already talked about what entropy is in the last video, and so we're going to apply that to some other things. So before we get started, actually, have your equation sheet out today and also grab your calculator. So let's get started. All right, so let's just review what the concept of entropy is referring to. Remember, guys, entropy is a measure of chaos, disorder. And there are laws of thermodynamics, and the third law of thermodynamics says that the entropy of a perfect crystal, a perfect ionic crystal at 0 Kelvin, that's absolute zero, that entropy is 0. Essentially, that's saying that an ionic compound at absolute 0 has no disorder to it. It is perfect, flawless. Now, if you're in the know, absolute 0 has yet to be achieved at this point. So everything at any other temperature above absolute 0 will have some disorder. Okay, so remember, entropy is abbreviated with the variable S. So entropy values for all substances, elements, compounds, everything at any other temperature other than absolute 0 will be greater than 0. Now, no matter what textbook you are using, you will have a list of what are called standard absolute entropies listed. Usually it's in the back of your textbook. In the textbook that we use, it's in what's called Appendix C. You will have a list of all these different elements and compounds, and their absolute entropy values will be listed. And those numbers are essentially a measure of that element or compound's disorder. Now, how you put a number to how messy something is, I really don't know. But all of you should have access to some sort of table of values. Okay. And as I said, these values are a reflection of the disorder, the chaos of those particular substances. If you happen to look at your table of values, absolute entropies, you will notice that pure elements have lower entropy values than large molecules. The more complex the molecule, the larger, the more atoms that are involved, are going to have higher values of entropy because there's a lot more ways for those molecules to be arranged, whereas simple pure elements that are just atoms are relatively simple. Now, actually, let me go back up. Let me say something about these values in these tables, whether it's your teacher has given you a chart with these values, or if you're using a chart from the back of your textbook. You are not expected to memorize any of those values. So if you need an absolute entropy value for a particular element or compound, the AP exam has to give it to you, like write in the question. And we'll see an example of that in just a second. One of the uses that you might use those values out of the chart is with this formula right here. It looks very complex, but it's actually not. We have actually seen this kind of a formula before, back in Unit 6. But in Unit 6, the only difference here was that it was calculating delta H for a reaction, the change in enthalpy. But let me just refresh your memory, guys. On your equation sheet, okay, there is a section called thermodynamics / electrochemistry, and these equations are in there. You don't have to memorize them. Okay, so they are there for you. But let's just refresh our memories on what these symbols mean, okay? Delta, of course, means change. Delta S, change in entropy for a particular reaction. Sigma, if you're remembering, means summation. The sum of the entropy values for your products. And this guy right here means you need to use a balanced equation. That little n stands for moles, okay, which translates into you would multiply these entropies times any coefficients that you see in your balanced equation. But it's essentially the entropy, the total entropy of your products minus the total entropy of your reactants. And as I said, we have done a calculation just like this before, except we were using enthalpy, heat values. Same process though. So let's look at an example. This is an example of a multiple choice question. But we have a balanced equation up at the top, and it says the table below provides approximate entropy values for the reactants and the products. Which of the following is the approximate delta S for this reaction? So delta S for the reaction is equal to, and I put a big set of brackets. Let's look at our product side first. PBI2 is my first product. I find its entropy value in the chart. It's 175. Look back at the equation. I see that it has a coefficient of 1, so I don't have to multiply times anything. So 175 plus, I see that my other product has a coefficient of 2, so 2 times, let's find KNO3 in the chart. It's at the very bottom. 2 times 150. And then I'm going to close the brackets. That is the total entropy of my products. So it's products minus, let's tally up our reactants. My first reactant, lead nitrate, there's only one, it has a coefficient of 1, and its value in the chart is 250. And my other reactant is Ki, there's 2 of them. 2 times 125. You type all of that in, ladies and gentlemen, and you're going to get negative 25 joules per Kelvin. Oh. Okay, so A is going to be my answer. You could have done this with a calculator. These are relatively friendly numbers that I would hope you could work with in your head. But as I said, guys, you do not have to memorize any value out of those thermodynamic charts. The AP exam will give you any numbers that you would need. Okay, there's just a much neater way of looking at that work that we just did. So what I would like for you guys to do is pause your video and try this one on your own. This is more like a free response that has 2 separate questions. Give it a try. All right, so we're given a balanced equation. Okay, we're told the delta H value, which is negative. I know this doesn't really have to do with the problem, but we'll need this information in the next unit. So let's just review. Remember that a negative delta H value indicates an exothermic reaction. Heat is released. Okay. Part A says predict the sign of delta S for this reaction and justify your answer. Okay. Meaning they don't want us to calculate it yet. This is more like what we covered in Unit 9.1. Just looking at the balanced equation, what would you predict for that sign for delta S? So I said delta S will be negative. Now let's remember what that means. A negative delta S means the process, whatever it is becoming more organized. My justification was that a solid and gaseous reactants are being converted into one solid product. Okay, so not only have I mentioned the fact that two things are becoming one, but I've also talked about the states of matter, and solids, of course, have the least amount of entropy. Part B then says, okay, go ahead and calculate it using the values in the table. And so let me show you my work here. Products minus reactants. And indeed, it is a negative value, negative 181.1 joules per mole Kelvin. So there is my final answer. So this was a relatively short and simple little subunit. So I hope you have learned a little something today, and I look forward to seeing you next time.